Enabling effective communication within any complex organization is a big job. At the University of Texas Medical Branch, supporting computer networks and communication infrastructure is vital to providing the highest level of care and service to our patients, to training our students, supporting discovery, and conducting our business. I'm Darwin Van Dyke, Director with the UTMB Health Information and Technology Services team. Tonight's Thought Leaders lecture explores NASA's Deep Space Network, the DSN, and its role in helping NASA communicate with spacecraft circling our planet or traveling throughout the universe. From the stations in the United States, Australia, and Spain, the DSN employs massive radio antennas to communicate with, control, track, and monitor spacecraft. It enables data from the vehicles to return to Earth for further investigation and discovery. It was the DSN that provided NASA scientists a close-up look at the surface of Mars. The DSN enables scientists to probe the nature of asteroids and the interiors of planets and moons. It was also the DSN that allowed many of us a front-row seat to Neil Armstrong's walk on the moon and many of the other amazing images of space that have been shared in the years since. I know from experience some of the challenges that professionals in our field face keeping people online and connected and the data flowing on Earth. I am fascinated and look forward to learning about how NASA manages it across the millions of miles and hostile environment of space. Thank you for joining us for this great session.
Hello, I'm William T. Harris, President and CEO of Space Center Houston. We're a nonprofit and immersive space exploration learning destination with the purpose of bringing people and space closer together. We're also the official visitor center of NASA Johnson Space Center and help share the story of human space exploration with more than 1.3 million visitors annually from around the world. Thank you for joining Space Center Houston's Thought Leader Series, Deep Space Network, presented by the University of Texas Medical Branch. Our Thought Leader Series brings you space and science experts from around the country to provide insights and perspectives on space exploration. NASA Johnson Space Center, partner government agencies, and commercial partners are focused on the Artemis program for lunar exploration, a critical part of our lunar research. Our thought leaders are subject matter experts who discuss the significance of their research and findings to enable us to better understand our solar system, universe, and future exploration missions. Here at Space Center Houston, we believe science learning and space exploration are for everyone, and are proud to celebrate 31 years as a premier learning center for the Houston community and space industry. To plan your journey with us, go to spacecenter.org to purchase your time tickets ahead of your visit and review our Know Before You Go guide for additional tips to maximize your fun. And now I introduce you to our Thought Leader series on Deep Space Network presented by UTMB. We're delighted to be joined by Dr. Alfonso Faria, who received his bachelor's in science and master's in science with a focus in mechanical engineering from the National University of Mexico, or UNAM, in 1983 and 84, respectively. He also received his PhD in mechanical engineering from the University of Wisconsin in 1987. Dr. Faria has worked at the Jet Propulsion Laboratory, or JPL, for more than 30 years, where his duties have included the structural design and analysis of 34-meter antennas, and the design and development of inflatable structures for radar applications. From 1998 through 2004, he was the supervisor for the Antenna Structural and Mechanical Engineering Group in charge of JPL's Deep Space Network antennas, or popularly known as DSN. From 2004 through 2006, Dr. Faria was the Space Interferometer Mission Lead for the Structural Analysis Team. He also worked as the lead analyst for the ChemMin X-ray source, an instrument currently on the Mars Science Laboratory Curiosity. He also worked as a product element manager for the mechanical ground support equipment of a Department of Defense sponsored program at JPL. He was also the lead mechanical systems engineer for the Sunjammer project, a spaceborne solar sail program, and the mechanical engineer for the Miri Cricooler flying on the James Webb Space Telescope mission. Finally, after working on the quote-unquote dark side, Dr. Faria was relocated to Spain from 2018 through 2021 to work at the Madrid Deep Space Communications Complex as the DSN Aperture Enhancement Project Implementation Manager during the installation of 2 tracking stations. Currently, he supports DAEP as a system engineer for DSN projects and the power upgrades at MDSCC. Our next speaker is Jermaine Assis, DAEP Systems Engineer. Jermaine graduated from the University of California, San Diego with a bachelor's in structural engineering and earned a master of civil engineering from the California Polytech State University, Pomona in 2013 and 2016, respectively. Jermaine joined the Jet Propulsion Laboratory in 2016 and the Antenna Structural Mechanical Group as the Cognizant Design Structural Engineer after several years of working under JPL's Deep Space Network, or DSN, operations and maintenance subcontract. She's been heavily involved in the construction of the DSN Aperture Enhancement Project, DSS 56, and DSS 53 antennas in Madrid, Spain, and is now the contract technical manager for the DSS 23 pedestal and antenna subcontract being developed in Goldstone, California. She also started planning efforts for the DSS 33 project for the construction of a new tracking station in Canberra, Australia. In addition, she was previously led several DSN design efforts, such as the Beam Wave Guide excavation design, 70-meter, and 34-meter roof repairs, 70-meter apron replacement design, DSS 54 emergency column design, and is the DSN earthquake emergency response civil lead. Jermaine has conducted concrete, seismic, geotechnical, costing studies, and DSN metrology studies. Currently, she continues to support DAEP as a system engineer and helps support the planning and construction of the DAEP antennas to meet missions. Our panelists will now provide more information about their backgrounds, the scope of their work, and followed by a joint presentation on the Deep Space Network. First, we'll hear from Dr. Faria.
Hello. Thank you very much, William, for the introduction, and thank you for having us here. I work for the NASA Jet Propulsion Laboratory, and this year we're celebrating 60 years of the NASA Deep Space Network. So after this talk, hopefully you understand a little bit better of the functions and the history of the DSN. So a little bit about me. I was born and raised in Mexico City. I came to the United States when I was 24 years old. I studied my bachelor's and my master's degree at the National University of Mexico in Mexico City. And then I came over to the United States to study my PhD at the University of Wisconsin in Milwaukee. After I graduated from the university, I held a few teaching positions at the different universities at the UNAM, at the UWM, and I also taught some courses at the Cal Poly Pomona, where Jermaine, our other speaker, received her master's. I also worked at a power company in Milwaukee called Cooper Power Systems for about 4 years before I came to the Jet Propulsion Laboratory in 1992. So I've been working for about 32 years over here. It's been a very fantastic experience throughout my professional career. So here at JPL, I've held many different roles and responsibilities. As you can see from my curriculum, I cannot get bored easy, and I jump from one area to another area. I started as a DSN mechanical engineer. I did a lot of analysis work for the antennas. I was fortunate enough to work on the new model of antennas, which has become our workhorse, which are called the 34-meter beam guide antennas. And these antennas are very flexible, and these are the ones that we have been constructing and fabricating in the last few years. I also work on inflatable structures, and this was more of a research and development project where we tried to come up with a structure that will be collapsed here in Earth, and then once you send it over to space, you inflate it, and you can create these very massive structures that can support, in this case, radars for space applications. When I was a group supervisor for the antenna mechanical group, I had the fortune of working for the 50-meter radio telescope called the GTM or LMT, the Large Millimeter Telescope, which is a telescope that was designed and installed in Mexico with a joint venture with the University of Massachusetts. So that gave me an opportunity to travel back to Mexico, visit family, but also, accomplish this major scientific instrument on top of a mountain in Mexico. Then I work also on, as William mentioned, on the X-ray source, which is installed on a Chemin instrument on MSL. This instrument basically takes samples of the Mars soil and puts them in little windows. It's bombarded by the X-ray to determine the soil composition in Mars. So that was a very interesting project I worked on. Later on, I worked also on some various other projects. One of them was Juno. I was working on the spacecraft bus as the structural lead, which was assembled at Lockheed Martin. And currently we have Juno orbiting Jupiter, trying to determine the atmosphere, whether we have a solid core on Jupiter, and also studying some of the different fringes that we have on Jupiter. I also worked on some DoD projects, which were not necessarily secret projects, but just in general, trying to demonstrate some capabilities. And as you can see, this one right here looks very much like a James Webb telescope. We were just trying to make sure that the feasibility of the telescope before it was sent out to space. And as William mentioned, I worked on solar sail. This was a project with NASA. Trying to build a 10-meter by 10-meter solar sail that eventually would be sent over to space with a little spacecraft on the back, and the propulsion would be basically the solar wind. One of the most interesting projects I worked on is the MIRI cryocooler. This is a cryocooler used in the MIRI instrument, which is one of the three main instruments in the James Webb telescope. And if you've seen some of the amazing pictures that James Webb has sent out, it's basically these images have to be cooled down to about 7 degrees Kelvin. And in order to do that, we need this cryocooler that works with helium. And that was developed over at Northrop Grumman and JPL. And one of those people that you see over there with the blue coats and the white hoods, it's me over there during the assembly of this cryocooler. And finally, one of my latest projects has been the construction of these two new antennas in Spain, these 34-meter beam waveguide antennas, to increase the capabilities of the Deep Space Network for our future missions.
Hello, everyone. It truly is a pleasure being here today with you all. A little background about myself. I received my Bachelor's of Science in Structural Engineering from the University of California, San Diego, and my Master's of Science from the California Polytechnic University of Pomona. I since joined the Deep Space Network in 2013 as a civil operations engineer and joined JPL in 2016 as a structural engineer. So I've been working in the DSN for roughly 10 years now. Currently, as William mentioned, I am the system engineer for the DSN Aperture Enhancement Program alongside Alfonso. And just a little personal about myself, on my free time, I do love to travel. I sing, cook, and I love to play volleyball. Now, a little bit about the work I do. I truly love being part of the DSN, and I've learned so much along the way. As I worked for the DSN, I've been part of the earthquake inspection and mitigation teams. I've completed road repairs, designed sewage systems, upgraded buildings to meet seismic codes, and ensured racks and floors are braced properly. You know, California does have a higher chance of earthquakes, and you can see those pictures in the slides at the very bottom. As part of the DEP team, I have completed excavation designs and implementations, updated pedestal drawings, and oversaw several concrete placements, reviewed critical lifts and antenna components, and completed several repairs to concrete during the construction phases to meet our required specifications. So just one of my favorite things about being an engineer is being part of the inception team and the developing the design drawings and specifications, and then really seeing it all come to life. So today's focus will be primarily about the Deep Space Network, but I want to talk a little bit about the history of JPL first. In the 1930s, a group of grad students from the California Institute of Technology, Caltech, and two amateur rocket enthusiasts performed experiments with rockets, and due to issues with noise and safety, they relocated to the foothills in Pasadena, California. In 1943, the Caltech team submitted a proposal to the Army and referred to their organization as the Jet Propulsion Laboratory. During World War II, the U.S. Department of Defense sponsored the work at Caltech for development of rockets and missiles. The main objective of JPL is a robotic exploration of the solar system, and it is also responsible for operating the DSN. After the war, a rivalry between the USA and Russia started due to the space race. So Russia first launched its first satellites into space in October of 1957. And in order for JPL to catch up, we built the Explorer 1 and launched it January of 1958, the year following. That same year, the U.S. government established NASA, and JPL was transferred from the U.S. Army to NASA.
So today we're going to focus on the 60 years of communication and discovery. As I mentioned before, the DSN is celebrating 60 years of operation. You know, DSN is our connection to space. It consists of very large antennas, and they're located about 120 degrees apart in the Earth. So as the Earth rotates, we always have communication with the spacecraft we send out to explore the different planets and space. Since 1963, NASA has directed JPL to basically track and follow these spacecraft into the different planets and into the edge of our solar system. And we're going to be talking about some of these spacecraft and how far they have gone so far. As I mentioned to you, we have 3 tracking stations. We have tracking station here in California. We had one in Madrid and one in Canberra in Australia. They are 120 degrees apart. So as the Earth rotates, we always have communication with these spacecraft. So in 1958, the first ever antenna for space communication, it was named for the Pioneer moon missions. It was built in Goldstone, California. It received the first signal from a Pioneer 3. So Pioneers were a spacecraft that were sent out to explore the moon ahead of man going into moon exploration. So this first communication was very important in the development of the Deep Space Network. At this time, in 1958, you know, we were still part of the Army. NASA was not formed until later in 1958. So in 1960, a new antenna at Goldstone was able to transmit rather than just receive the information from the stuff from space. And the first communications was basically a recording from President Eisenhower that was sent from California to New Jersey. This project was called the ECHO project, which was an experiment where we sent a huge balloon into space, and the communication basically bounced off of that balloon into the next receiving antenna, which was in New Jersey. And that's why it was called ECHO, because basically it was bouncing the signal from California into this huge balloon in space down into New Jersey for our first communication. In 1962, we have a program called the Ranger missions. Again, Ranger missions were sent out into the moon to basically take pictures of the surface of the moon to see if it was feasible for man to land on the moon. Later on, these Ranger missions were actually crashing into the moon, and as they were crashing into the moon, they were taking pictures of the moon, again, basically to see if there was enough solid surface for man to be able to land in the moon. In the picture on the left, you could actually see a Ranger 1 spacecraft, and several of those were not successful, but many of those were. And that's how that was the contribution of JPL to the moon exploration. Now, in 1963, our former director, William Pickering, officially signed an agreement and established the DSN as a global system of giant antennas for spacecraft tracking and communication. And that was basically how DSN was born, and that's why we're celebrating this year 60 years of the DSN. In 1966, preparation for future and more sophisticated spacecraft at Goldstone, we built a 210-foot antenna. It's a 64-meter radio telescope and communications antenna that was built at Goldstone. Then in 1969, an antenna at Honeysuckle Creek in Australia. It's the one that basically received the first images from Neil Armstrong setting foot on the surface of the moon. So in the images that you see there on the left, you can see the huge size of a 64-meter antenna. That was the original size of this antenna. We're going to talk a little bit more about that later. And then on the image on the right, you could see some of the images that were received first in the stations in Australia. Then in the 1970s, as our demand for DSN support was increasing, new antennas had to be built, and then we started doing something called arraying, where we started combining several antennas to receive signals to create a bigger aperture. In 1973, we built our 210-foot antenna, our 64-meter DSN antenna in the Madrid complex, and it was just in time for Pioneer 10. That was his first ever encounter with Jupiter. And then in 1977, taking advantage of the rare planetary alignment, the twin Voyager spacecraft were launched to explore the outer planets. So this became a very big challenge for the DSN because it required a lot of power to communicate with these long distance spacecraft. In 1984, we constructed a series of antennas called the high efficiency antennas. So these were basically our first series of 34-meter antennas that being able to communicate at X-band frequency, which is a shorter band than the previous L-band and S-band communications. That means more information was coming in to these antennas. And then in 1987, remember our 64-meter antennas, they were not big enough, so we needed to expand them. So we created a 70-meter antenna. So it was a very difficult feat for engineering, using the existing structure that we have for a 64-meter antenna, expanding it to a 70-meter antenna. We were now be able to hear very weak signals that were, billion or a trillion of a watt being sent by these very far away spacecraft that we have now in space. Like in 1989, the Voyager 2 made its closest approach during a flyby of Neptune, and using the 70-meter antenna now, it was able to do some radio science into Neptune's atmosphere and rings. So in the images, you can see on the left, our newer high efficiency antennas. You can see a little cone in the center of the antenna, and that's where the signal comes in. Later on, we're going to talk about the new generation of antennas are the beam waveguide antennas, which are missing that little cone in the center. Then you can see the construction, the big scaffolding that was required to expand that 64-meter antenna into a 70-meter antenna. Those antennas are still in service. So it's just amazing, the engineering that goes into analyzing and designing these huge radio telescopes. And the image on the right, you could see Voyager image around Neptune. Then in the 90s, Voyager takes its last images, the first partial family portrait of the solar system. It was 6.4 billion kilometers away, and we were receiving all those images back. And currently, the images that we have for Neptune and Uranus are basically the images that we have seen close by from the Voyager spacecraft. In 1991, the first antenna to use beam waveguide technology. was routed signals from a room that was basically in the basement of the antenna, and it greatly improved the network efficiency. And that antenna, which is DSS-13, currently at Goldstone, California, was the antenna that we basically use as a basis for the newer series of antennas, our 34-meter antennas. In 1995, Galileo spacecraft is a spacecraft that was sent out to explore Jupiter. But unfortunately, the major antenna in Galileo didn't deploy correctly. It's a long story, but originally Galileo was going to be launched with a space shuttle, but then we had the tragedy of the Columbia shuttle. So the spacecraft had to wait basically on the launch pad for a long time until the next space shuttle was able to send out. By the time it was sent out, there were some anomalies and the large gain antenna was not able to deploy. So the only communication we had with Galileo was through the smaller antenna, and the efficiency was very, very low. But as always at JPL, we don't see problems, we see opportunities. And the opportunity that came out of that was basically how do we get the most data from a smaller antenna into the DSN and try to save this mission. And out of that came a lot of data compression algorithms and communication algorithms to try to bring in as much information as we could. And thanks to that, we have CD players and CDs and all that that uses compression technology, thanks to basically a problem we had with one of our spacecraft. 1997, we got an image from Sojourner, which was the first Mars rover that JPL successfully launched to Mars. It was a very small rover, but it enabled us to prove some technology that we can indeed send additional spacecraft into Mars. This is not the first spacecraft that landed in Mars. We had the Vikings back in the 70s, but this is the first rover that we had in the surface of Mars. And then moving into the 2000s, 2003, we had a lot of spacecraft now orbiting around the Earth. We have spacecraft going into different planets. We have the Voyagers going into interstellar space. So we need to construct new 34-meter antennas. So in 2003, we built a new antenna, a new 34-meter antenna in Spain. 2006, we sent information so that we can start arraying some antennas. Again, like I mentioned before, we have several antennas that we can synchronize together to create a very large aperture. In 2008, we received some lunar image data that we collected using radio science with the DSN. Like I said, DSN, can be used as communications. We can also use DSN for science experiments and science contributions. On your left, you can see the Madrid Deep Space Communications Complex back in 2003. You can see several of their antennas. In there, we have a 70-meter antenna. We have several 34-meter antennas. In the image on the center, we're working with arraying some of these smaller antennas, in this case, 6-meter antennas. And the idea was that we could have hundreds of these little antennas and arraying them to make a very large aperture for communications. And then on the right, we have just an illustration of a SpaceX Starship for human lander. And currently, and we talk about Artemis, we're looking at going back to the moon to explore the moon and hopefully use the moon as a launching pad for our Mars exploration. Going to 2012, we received signals from Voyager 1 at 12 billion miles away and indicated that our 36-year-old spacecraft is the first human-made object to enter interstellar space. Basically, we're beyond our solar system into interstellar space. And nowadays, we're still receiving signals from both Voyager 1 and Voyager 2. The communication currently, it takes about little over 18 hours one way to communicate with the spacecraft. So basically, it's almost a day before we can reach the spacecraft, and almost day and a half to 2 days to receive communication back and forth from our Voyager spacecraft. Between 2010 and 2016, as part of the Deep Space Network Aperture Enhancement Program, the DAEP, we built 2 new 34-meter beam waveguide antennas at Canberra Deep Space Communication Complex in Australia, which are currently now operational. And in between 2017 and 2021, again under the DAEP program, we started building 2 new 34-meter beam waveguide antennas at the Madrid Communication Complex. And as I mentioned before, I spent 3 years there during the construction of these 2 antennas. One was commissioned in 2020, and the second one was commissioned in 2021. The main concern basically was this was done during COVID time. So a lot of the testing has to be done remotely with JPL rather than having JPL engineers travel to Spain. In 2022, after a successful launch of the James Webb Telescope, the DSN has been supporting the trajectory course of the JWST as well as the telescope's operations. Also last year, we supported Artemis 1 mission. As you know, Artemis 1, basically it's a launch vehicle that goes around the moon and back without any human presence. Artemis 2 is going to have astronauts basically launch around the moon and back. And the program for Artemis 3 is to have actually humans land on the moon again. And DSN hopefully will be supporting these with our ground antennas for communication. And 2023, a new beam waveguide antenna is being built over in Goldstone. It's called DSS-23. And currently, we have built the pedestal, and we're currently fabricating the structure. And we're going to start working on the facilities at Goldstone. So what is the DSN? It's our messaging, it's our communication between the Earth and the spacecraft that we send out to deep space. So this space is distance far enough from Earth such that the spacecraft will always be in view of any of our antennas. That's why we have our 3 tracking stations. So as Earth rotates, we always have communication with these far away spacecraft. So the information that we communicate, we have inbound communication. So basically we receive some of these signals from a spacecraft, and we have science data, we have observations, we have pictures, we have data files, we have experiment results, we have spacecraft health information, diagnosis results, fault errors, location and navigation information from these spacecraft. But we also, with these large antennas, we're able to send communications outbound. And we can send commands for test and diagnosis of our spacecraft. We can do navigation corrections. If we see that our spacecraft is not going in the right direction, we can send corrections to that. We can do task preparation and changes. We can activate instruments. We have cameras, we have all kinds of instruments that we can turn on and we can turn off directly from the Earth. Activity commanding, we have all these rovers roaming in Mars, for example, and we can communicate with them and tell them the direction they need to go to, what rocks they need to perforate, they need to analyze, all kinds of things that we can command our spacecraft to do. We can also request diagnosis on how our spacecraft is doing, and we can reprogram them, during a particular mission, if we're orbiting around, say, Jupiter, and then we say, you know what, why don't we take a closer look at one of the moons in Jupiter? We can reprogram that orbit to send the spacecraft in a different orbit to get closer to one of the moons that we're more interested in. So it's very powerful, the communication that we have with the DSN. We can see, again, telecommunications. We have uplink, we can command. We also have downlink, which we call telemetry. We utilize different frequencies. We have S-band, which is a very large frequency band, but we also have X-band and also Ka band for communication with them. We have, of course, tracking. We have to know where our spacecraft are all the time. Otherwise, we can lose them very easy in space. So we always have communication with the spacecraft, and we try to guess where the trajectory is going so that next time we communicate with them, we know exactly where they are. So it's very important for us to keep always tabs on all our spacecraft. And with all the spacecraft that we have, it's so important to have many apertures communicated with them. And like I mentioned before, it's not only communicating with spacecraft, we can also do science with these very large telescopes. You know, all the planets and all the objects in space, they emit a radio signal. So we can capture that radio signal and analyze it to determine probably composition of the particular object that we see in space, or other things that we're looking for science.
All right. So now that you understand more about the history of the DSN and what the DSN is, let's jump into each of its deep space communication complexes located in the USA, Spain, and Australia. Okay, so Goldstone was the first deep space communications complex, otherwise known as GDSCC. In 1958, the Pioneer Station DSS-11, shown on the top left here, a 26-meter polar mounted antenna, was the first deep space antenna to be constructed at Goldstone. And then construction of the DSS-14 azimuth elevation 64-meter antenna started in October of 1963, which is shown in the top middle picture. The DSS-14 antenna was upgraded to a 70-meter, 230 feet diameter in 1988. And then this was to increase the sensitivity in support of the Voyager 2 spacecraft and its encounter with the planet Neptune. The complex has a total of 9 antennas, and one is currently under construction, which we'll talk about a little later today, DSS-23. The Madrid Deep Space Communications Complex, MDSCC, is the only NASA installation in Spain that came about through a government-to-government agreement and the collaboration of INTA. ISTEFE operates and maintains the complex with approximately 90 workers, and the complex has a total of 6 antennas currently. The Canberra Deep Space Communications Complex started operations in 1964 to support the Mariner 4 mission with a 26-meter diameter antenna. And in 1969, the construction of the 64-meter diameter antenna was started, which is 6 times more sensitive than the 26-meter. The complex has a total of 7 antennas. All right, so as mentioned, in the DSN, we have 2 basic antenna sizes, one of which is a 70-meter diameter, and this weighs about 9 million pounds above its supporting concrete pedestal. So the other antenna is a 34-meter beam waveguide antenna, or HEF. There is one 70-meter antenna and at least 4 34-meter antennas at each of the 3 DSN stations. In the photo on the left, you can see how our 70-meter antenna would look like inside a football stadium. It kind of provides you a reference to how small the people look compared to the size of the antenna itself. Kind of astounding. So on the right is also another comparison where you will see the pedestal itself is nearly the size of a 2-story 6-bedroom house. For the 34-meter antenna, there are 2 designs, the older high-efficiency antenna known as a HEF and the newer design known as a beam waveguide BWG antenna, and these weigh a bit less than 1 million pounds each. The image here shows key aspects of a DSS-34 beam waveguide antenna. The 34-meter antennas are constructed a little differently. The pedestal foundation is constructed underground. Inside the pedestal, you have a mezzanine structure and all the microwave electronics and some of the mirrors. Above the pedestal, you have the azimuth track, which the antenna rides on with 4 azimuth wheels. And in the photo on the left here, you'll see the pathway that shows how we receive data from the spacecrafts. Once a signal is received, it bounces off the shape surface reflector to the subreflector. It then goes through a series of mirrors located in the beam waveguide to the pedestal, where the data is then sent to be processed. Now that you know a little bit about the various sites and antennas, let's talk about the project Alfonso and I have mentioned previously, the Deep Space Network Aperture Enhancement Project, DAP. With the DSN 70 meters approaching 60 years in service, repairs and maintenance become more difficult and costly. DAP started in 2009 and will replace the 70-meter antennas with arrays of 4 34-meter, which is 111 feet beam waveguides. The 34-meter antennas will be equal to the performance of a 70-meter antenna while providing greater flexibility and reliability at a lower cost. So the Deep Space Station DSS-35 was the first of the 34-meter antennas for DAP and was declared operational in October of 2015, followed by DSS-36 in October of 2016, both of which were constructed in Canberra. In January of 2021, DSS-56 became operational, and in February of 22, DSS-53 became operational, both of which were constructed in Madrid. So we will continue constructing 4 34-meter beam waveguides at each site until we complete the effort in 2029. So here we have 3 DAP antennas that are being worked by several teams and are currently under construction or in planning phases. So on the left, you'll see the DSS-23 antenna, which will be operational April of 2026. Currently, the pedestal, as Alfonso has mentioned, has been constructed and backfilled at this point. The azimuth track is being placed and aligned currently. Inside the pedestal, you'll see that the mezzanine structure is starting to be built. At the fabrication facility, they have completed the inspection and assembly of the alidade structure itself. So now it's in disassembly and it's getting painted. And then on the left, you'll see the photo of the reflector structure. And that is also being inspected currently by our engineers this week. Following this, it'll be disassembled, painted, and then all parts will be shipped to California for assembly on site. Moving on to DSS-54, this antenna will be operational in December of 2026. Currently, the site is excavated already, and they're working on the patrol roads, installing V-ditches, and they'll be putting the leveling layer on soon, and then we will begin construction in about a year. For DSS-33, we completed the geotechnical investigation and the site selection has been completed at this point. So now we're moving on to the planning phases so we can get the rest of the work completed as well. That antenna will be operational October of 2029. So now let's talk about how it all comes together. We have several teams working all the design phases. As you saw here, the pedestal excavation is completed, the pedestal gets constructed, you have the concrete placed, you already have the ramp placed, and now they're in the backfilling process. Once the pedestal is backfilled, then you'll have parts starting to arrive from wherever the antenna is being fabricated. And as you see here, they place the azimuth track and pintle. Now they're starting with the erection of the alidade structure. And now they did the erection of the reflector. Then we have a critical lift happening. They lifted the reflector and quadrupod structure on top of the antenna. And now they're also doing facilities work on the ground. Also, during this time, you see the antenna is moving several times because they're completing alignments to make sure that everything is meeting the JPL requirements for the antenna. And INT testing also starts at this time. What you see on the ground is just a lot of the facilities works taking place. The apron was placed, the fence, security fence is placed. And you see the antenna moving various times due to the INT happening. Although our DSN antennas were designed decades ago and continue functioning very well today due to future demands for higher amounts of data going through them, especially with missions putting humans back on the moon and on Mars, we are currently working on the design of an optical antenna that will have various frequencies to use and each transferring much larger volumes of data than today. With human missions, knowing the health of our astronauts and monitoring their progress will be extremely important in addition to our science goals and spacecraft condition. As you see on the left, the optical reflector is nestled in the central portion of the beam waveguide antenna. So we have the two antennas in one, a radio frequency and an optical antenna.
So how does the antenna work? Basically, it's like your cell phone. That would be the easiest analogy. You know, you have your cell phone on your hand, and then you have an antenna that the cell phone communicates with, and then that antenna relays the information back to the other person that have the cell phone. And all of this is transferred through radio waves. Basically the same principle that we have on our antennas. We have the project scientists that are reviewing the data. We have our deep space network antenna that is sending and receiving the radio waves either from a spacecraft or from radio science. These radio waves, as you can imagine, you know, are of different sizes and power. The antenna is, because we're on the ground, we're able to send radio waves with very high power. We have very high powerful transmitters that we can utilize. But unfortunately, the spacecraft, because it's limited in size and in electrical power, they can only send very weak signals. So we receive those signals into our antennas, and we have to process them and filter all the noise out in order to come up with the communication that the spacecraft is trying to send back to us. And that's a basic principle of the communications with the antennas. In the next video, you will see how these radio waves are utilized and are coming into our antennas. You can have a little better understanding on how the DSN operates.
NASA has dozens of robotic spacecraft exploring our solar system and beyond. Scientists and engineers communicate with and navigate faraway spacecraft using the Deep Space Network, NASA's international collection of giant radio antennas used to communicate with spacecraft at the moon and beyond. But the Deep Space Network, or DSN, is more than just a messaging service. In fact, scientists use the DSN to perform radio and gravity science experiments. But what is radio and gravity science, and how can it help us learn more about the planets, moons, and other small bodies in our solar system? We're all familiar with gravity. It's the force by which an object attracts other objects, such as a planet pulling a spacecraft toward it. Gravity is also the force that keeps all of the planets in orbit around the sun. Here on Earth, we experience this every day. If you drop an object, it will accelerate toward the ground because Earth's gravity causes it to fall faster and faster, and the acceleration of a spacecraft toward a planet depends on the mass of the planet. Less mass means less gravitational pull. These properties of gravity, combined with our understanding of radio waves, help us use gravity to study other planetary bodies in our solar system. After reaching its destination, a spacecraft uses radio antennas to communicate with the Deep Space Network on Earth, which in turn transmits radio signals back to the spacecraft. Every spacecraft travels in a predetermined path, emitting radio signals as it orbits around its target. Scientists and engineers can infer the spacecraft's location and how fast it's going by measuring changes in the spacecraft's radio signal frequency. This is made possible by the Doppler effect, the same phenomenon that causes a siren to sound different as it travels towards and away from you. The Doppler phenomenon is observed here when the spacecraft and the DSN antenna move in relation to each other. Differences between the frequency of radio signals sent by the spacecraft as it orbits and signals received on Earth give us details about the gravitational field of a planetary body. For example, if the gravity is slightly stronger, the spacecraft will accelerate slightly more. If gravity is slightly weaker, the spacecraft will accelerate slightly less. By developing a model of the planetary body's gravitational field, which can be mapped as a gravitational shape, scientists and researchers can deduce information about its internal structure, all while using the Deep Space Network. To learn more about the Deep Space Network, visit go.nasa.gov/about-DSN.
Hope you enjoyed that video. And also, I would recommend, if you would like to know how the current situation of the DSN is going, just have to visit the link shown on your screen. You will see this on your mobile or on your computer, and you will see how the antennas work, basically. In some cases where you could see the little rays going into the antenna, that means that the antenna is currently operational, either transmitting or receiving information. Also, in little letters above each of the antenna, you would see a name or some acronym for a particular spacecraft that it's currently tracking and following. So it's a very interesting website. I encourage you to basically mark it and go and visit. We can also see, for example, the current mission that was sent out, Psyche, was launched just last Friday. This is a spacecraft that's going to go and study an asteroid. It's a metal asteroid, and we're very interested in seeing what the configuration and the chemical components are of this particular spacecraft. So all of that you could learn out of this very interesting website. So as Jermaine explained to you, JPL is a Center for Excellence for Robotic Exploration of the Universe. And part of the JPL, we have DSN. JPL has sent out a lot of different missions throughout the many years. But the current missions, as you can see in this picture right here, we have over 40 missions that we're currently tracking. So you can see the demand of the DSN is very, very large because we have to communicate with all these spacecraft. We have to track all these spacecraft. We have to receive information, pictures, analysis of the instruments that they're doing. We also have to send commands to these spacecraft to, for the example, for the rovers to tell them where they need to go. We need to tell the different spacecraft if they need to do a maneuvering correction. So as you can see, the demand for the DSN is very, very high, and that's why the DAEP is so important to increase the capability of the Deep Space Network. As Jermaine has mentioned to you, we have built several new tracking stations in Canberra and Spain. We're currently building one more in Goldstone, and we're going to be building another one in Canberra. A question that we usually get is whether extraterrestrials exist, whether we have ETs, and whether we have detected ETs. You know, personally, I think it would be very egocentric of us to think that we're alone in the entire universe, you know, on the planet Earth. So I believe there's probably extraterrestrials somewhere out there. We don't know where, and we don't know what kind of form they have. But in terms of science and engineering, you know, JPL back in 1992 started working with the Search for Extraterrestrial Intelligence, the SETI program. We have a program called HRMS, which is a high resolution microwave survey. And basically what we were doing, we were scanning the sky with our large antenna at different frequencies, trying to detect any radio inputs from outer space. As we know, as we already explained before, every planet, every object in space emits radio waves. So we have to discern between those radio waves and any other radio frequencies that we would detect. We were targeting very weak signals for different stars or different planets. We did a sky survey to map the entire celestial sphere. But a few years back, the report stated that we have not identified any extraterrestrial intelligent signals in the range that we were tracking. It doesn't mean that they don't exist, but we did this tracking for several years. Many different frequencies, many different power outputs, but we couldn't detect any significant signals that we could say, those belong to some extraterrestrial intelligence. So we will keep looking, because I think it is important also for NASA to find out whether we have ETI or not. Um, as we know, NASA is looking for signs of life in Mars and other places. The current rover that we have in Mars, Perseverance, they're looking for signs of life in Mars. They're taking samples of the soils on Mars, and one of our future missions from JPL is our Mars sample return mission, which is going to be collecting those vials with soil from Mars, bringing them back to Earth and analyzing them to see if there was or if there is some kind of form of life in Mars. We also currently working on our Europa Clipper mission, which is going to be sending a spacecraft in next year to Europa to analyze the crust, the icy crust, and possibly the inside, which is supposed to have liquid water in Europa, and try to determine if there's some kind of life form in the planet. So we're continuing the exploration. We're not giving up. We're trying to find out if we can find some kind of life. As far as intelligence, that's going to be a little bit tougher for now.
Okay, so the DSN has helped with several commercialization contributions that you may be very familiar with. For example, we have helped with the pseudo noise codes used in your GPS and cell phones, medical scanners for detailed scans such as CT scans, two-way phase coherent Doppler examples of which we have our radar speed guns, and plate tectonic studies, which is a basis for fiber optics and cable TV. So the DSN has several capabilities and does help people in their everyday lives as well. If you are a DSN fanatic like I am, you can have the posters shown behind me or on the screen here by following the website shown. Also, if you're interested in further resources, we have provided links showing the DSN Antennas 360 virtual tour. How do we communicate with faraway spacecrafts? Where in the world is the DSN? Or you can play some games at the Uplink Downlink game link. And you can look into the Goldstone Apple Valley Radio Telescope project with the links provided herein. Thank you all for your time.
Well, thank you both. That was a very thorough presentation. I learned a tremendous amount about DSN and its background and all of its functions. We still have a little time that I want to ask you a few questions, and a number of things occurred to me during your presentation. And the first question is, how far out can a signal go? I'm amazed that we're still receiving signals from Voyager, which has left our known solar system. How far do you think we'll be able to detect signals, and especially with the newer technologies?
So I guess I can answer that question. Like I said, the Voyager spacecraft are billions of miles away from us already. The power that the signal comes out of Voyager is basically just a few watts. It's just like the light bulb in your refrigerator. It's very, very weak signal, and we can still detect that over here at the 70-meter antenna, which are the antennas that can still track those spacecraft. The signal comes here at thousands of a watt. So we think that we can still receive signals from outer space, probably from the Voyager spacecraft until probably 2030 or so, which is going to be even farther out. Now, as far as how far we can go, like I mentioned before, we have radio science. And so radio science basically receiving radio signals from different planets, from different stars in our, not only our solar system, but basically not our galaxy, but even beyond our galaxy. So I would say, thousands and thousands of, miles and billions of miles.
I have a question about artificial intelligence. Everyone is talking about AI or generative AI. Is that being applied in these technologies, particularly with the newer optical antenna that you've mentioned that will be used to support the Artemis missions and human missions? Are they currently being used, or are there plans to somehow use generative AI or some form of AI to support monitoring signals and transferring data?
Currently, I do not think we are using any AI for the optical development of the antennas. I don't know if there's future plans of use of it, but I haven't heard of anyone using AI at this point.
If I may add, just like Jermaine said, we currently don't have AI in the DSN, but it is being studied here at JPL, and eventually it's going to be part also of the DSN as it's being part of everything around us.
Yeah, I think we live in a time when AI is already present and a lot of people don't realize it. And it's used to help us with our preferences, and we use search engines. It's used in so many aspects of our life already. So I was curious how it could apply. It could create, I imagine, some greater efficiencies, especially when you're monitoring signals from so many different locations. So another big issue that there's a lot of conversation about right now is the volume of space junk that orbits Earth. And I'm wondering, does that affect your capabilities or abilities to send and receive signals? Is there interference that's happening because of the volume of so many satellites and other kind of vehicles orbiting Earth, and also space junk?
Yes, you're right about the amount of space junk. Fortunately for us, it hasn't been a major issue. I think the signals coming in through the atmosphere get distorted more than what we see on the space junk outside. But it is a concern, maybe not right now for the DSN, but in general, for all the spacecraft that we send out, and the spacecraft that NASA sends out.
There was also something you mentioned about some of the research you've done in the past with sails out that have been deployed, and you mentioned solar winds. So what are solar winds? Could you define those and explain how they are disruptive to some of the signals that we might be monitoring in space?
Yes, so basically, as you know, the sun, it's a combustion engine. It's flaring and sending out these big flares. So every time there's a flare, it's sending out photons, and those photons basically create what we call a solar wind. So it's just a compilation of these photons. When we have a solar sail, basically we're looking for a very large aperture that's going to be propelled by this solar wind. Basically, these photons impinging into this very large area and creating propulsion for that particular sail. As far as communications, of course, these photons, are going to disrupt our communication because they disturb the radio signals. When these little photons are impinging into the wave that's coming in, it's basically distorting that radio signal, and that's the reason our communications get distorted and affected.
Oh, that's fascinating. A lot of people don't realize that there's solar radiation, and that the sun is basically throwing off photons, right, which affect everything, even life here on Earth. Even though we have ozone in our magnetic field to help protect us, it still affects our telecommunications that we use every day. I'm curious, space exploration is more popular than ever, and it's reported that there are now some 77 government-affiliated space agencies around the world. Many are collaborating, some are not. They're pursuing their own interests. And so, and there are new antennas going up around, new satellites being deployed. Is there interference with signals that you're sending and receiving because of the proliferation of so many nations entering a space program and perhaps sending out their own waves in communications? Are you beginning to notice that, or is that a concern in the future?
Yeah, well, there is an agreement, an international agreement, and there are frequencies that are set for everything, for mobile communications, for radio communications, for TV, for space. And these bands of frequency are assigned to each country, basically, and to each entity. So NASA has been assigned a certain bandwidth in these particular frequencies. We operate at L band, at XS, KU, KA, and so we have been assigned certain frequencies. Now, to say that, there's some countries, and I'm not going to name the names, but there's some countries that don't affiliate to these conventions. And so we do get some interference with some of their communications with their satellites, and we have been able to detect some of their communications, inadvertently because of the they don't follow the regulations. But yeah, as more and more satellites are put up and more communications are being filled up, the band is getting narrower and narrower.
Well, I want to say thank you so much for joining us today and providing such a remarkable orientation and also answering questions about where we're trending in the future. As I say to everyone, this is the most exciting time to be part of exploration, and it's a critical role that you all fulfill in enabling us to explore space and also return humans to the moon and beyond. So I want to thank you both so much for joining us today for this Thought Leader Series Deep Space Network presented by UTMB. To our listeners, please visit our website at spacecenter.org to view past Thought Leader programs and other special presentations. Thank you again for joining us.
Well, thank you, William. We really appreciate the invitation to participate in this series. We really enjoyed it, and I hope everybody enjoys it as well. And, if you have any questions, we're always available.
Again, it truly was both of our pleasures being here, joining you in October's Thought Leader Series discussion about the DSN. And if you'd like to see any of our resources, please follow the links that we discussed.